Well, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to guide our steps today. Help us to understand just a little bit more about singular points and method of Frobenius, Lord. In your name I pray, Lord Jesus. Amen. All right, so picking back up where we were working on before the test, we're talking about series solutions, right? And up to this point, we've worked on problems that you could just plug a power series in and it works, right? And if you study the convergence of our answers, you'd have found out that they converged on the whole real line. Like, pretty sure the ones we've worked so far have been pretty nice examples. They didn't have singularities, with the exception of the Cauchy-Euler problem. All right, so today, to start with, I want to talk to you guys about the classification of singular points. This shouldn't take the whole class, so we'll do this for about the first half of class, and then hopefully the last half of class I'll talk to you guys about the method of Frobenius, which concerns how we solve a differential equation if we're faced with one of these particular singularities. And so here's the definition. Now the context here is just second order. We just work with second order ODEs in here. Like, you know, our universe is very small. We just work on the second order ODE problem. That's more than enough for us. We say x naught is, this is page 226 of my notes if you're tracking along here, is an ordinary point of y prime prime plus py prime plus qy equals to 0 if p and q are both analytic at x naught. Now, what does analytic mean? Do you guys know? No. So a function is analytic if it permits a power series representation at the point. All right. So can you guys give me an example of a function which is not analytic? I mean, there's sort of like, you know, esoteric things. Like you could look at the Dirichlet function. The Dirichlet function it's 1 for rational numbers and it's 0 for irrational numbers, right? So think about the graph of that. It would look like just two horizontal lines. Like it would almost appear, to the limits of my artistry, it would appear to be not a function because it looks like it's not single valued. But of course, you can't really draw all of the points that are both rational and irrational. So there's that kind of example. But what's more interesting is that there are actually functions which are smooth, but not analytic. And so the usual example people give is the thing that's like 0 here, and then it kind of just like that. And it's something, I forget this exactly, but I think the definition is something like this: 0 for x less than or equal to 0, and e to the, goodness gracious, I'll probably mess it up, but it's something like this, for x greater than 0. And so the thing about that is, if you study this, you can prove that the Taylor expansion for that function exists at the origin, and it's identically 0, right? So if you try to approximate that function with its power series at the origin, what's the graph of your Taylor series? The graph of the Taylor series at the origin for this thing, it's just this, right? That's the, you know, Taylor series at x naught equals to 0. It's the identically 0, and of course that does not represent the function, which is quite clearly non-zero on an open neighborhood of the origin, right? So this is the quintessential function which is smooth but not analytic. There are more functions which are smooth than functions which are analytic. Analytic is like, assuming that the power series of the function exists at each point in its domain. and can represent the function there. Now, in terms of engineering, you're pretty hard pressed to find stuff that's not analytic, right? Yeah. I mean, you do have like jump discontinuities. The function's not going to be analytic at that kind of point, right? Things like that, switches. So it's not completely esoteric, but look, they're back in the day. Like there's a book, I think Lagrange wrote a calculus book where he starts the book by saying, imagine a function, and then to define what a function is, he gives a power series. So like if I remember correctly, there's actually calculus books in previous times where the base assumption of the whole discussion is that every function's analytic. So I mean, if you do that, then you can define calculus by like the power rule on the power series and things like that. So anyway, how did I get off on this? One of your fault. Who did this? All right, I was not going to say all these things. Anyway, so that's an ordinary point. Just means that the coefficient functions of the differential equation are analytic. Now, we say x naught is a singular point, or sometimes we call it a singularity of y prime prime plus py prime plus qy equals to 0 if x naught is not an ordinary point. So every point is either an ordinary point or a singular point, right? One or the other. And then finally, a point x naught is a regular singular point. All right. If x naught is a singular point, however, x minus x naught times p of x and x minus x naught squared times q of x are analytic at x naught. In other words, what this means is that the coefficient functions, they behave badly at x naught, but not too badly, a regular singular point. So like, now if the singular point is not a regular singular point, then it's said to be an irregular singular point. But I don't even really have need to write that definition down because we're not going to learn how to solve differential equations at irregular singular points. There are elementary differential equations books which address that issue, but I don't have anything in my notes, and this will be plenty for us as it stands. So we'll just stick to regular singular points. Now, so some examples, yeah. So oftentimes the example comes to you in such a way that it's not in the right format to start with, right? So we might be faced with something like, x squared y prime prime plus 3x y prime plus, y equals to 0. In fact, we've looked at this kind of problem before, right? This is the Cauchy-Euler equation, right? The equally dimensional problem. We learned we could solve this by plugging y equals x to the power r into it, right? And then we had that like r times r minus 1 business. Remember that? So here, this isn't quite in the right format yet for my definition. So what we do is we take this and we trade it for y prime prime plus 3 over x y prime plus 1 over x squared y equals to 0, right? So this right here would be P. This right here would be Q in my definition. And you guys tell me, is X naught a ordinary point or a singular point? I'll start you out with X naught not equal to 0 is an what? So when can you find a power series expansion for a function, like generically speaking? If it's a rational function, the answer is anywhere in its domain, right? Like I have to work, I erased it, but that thing I had up there, you know, finding functions which are not analytic in the way that the previous one was, those are pretty hard to come by. This here, X naught is an ordinary point in this case because both 3 over x and 1 over x squared we could expand as a power series at X naught, right? Do you guys know how to do it? I mean, it doesn't much matter, I suppose, but for example, if I have 3 over x, I could rewrite that as 3 over, x naught plus x minus x naught, right? Adding 0. And then if I factor out an x naught, 3 divided by x naught divided by 1 plus parentheses x minus x naught over x naught. All right. Well, that's equal to like the sum n equals 0 to infinity of like 3 over x naught times minus 1 times minus 1 to the n divided by x naught to the power n times x minus x naught to the power n. What did I use there? Anybody? What's this thing we can replace a rational function with a power series like that? Okay, so you guys forgot? It's cool. A over 1 minus r is the sum. N equals 0 to infinity of like a r to the power n, right? So I'm identifying a is 3 over x naught, and my ratio is, in this case, like x minus x naught over x naught. I'm using the geometric series. So the geometric series straight away finds me a Maclaurin expansion for P. But you notice what I had to do for that calculation, all over the place, I had to do what? I had to divide by x naught, right? So can we do this? Can we do this when x is equal to 0? I mean, when x naught's equal to 0? Like, clearly not, right? So, but I don't even want to do it, but we could do a similar calculation. You could write down the Taylor expansion for 1 over x squared. If you want to, you just use Taylor's theorem, right? 1 over x naught squared plus, minus 2 over x naught cubed times x minus x naught, and so forth and so on, right? Just use the Taylor expansion. We can expand P and Q at a non-zero point. But what about 0? At 0, we can't, right? So as we look at P of x equals to 3 over x and Q of x equals to 1 over x squared, these are singular at x naught equals to 0, right? There's no fixing them there. I can't calculate the derivatives there. It's outside the domain of definition of the function, right? Agree? I hope. But what happens, but is this a regular singular point? How do we judge that? So notice that, x minus x naught times p of x and x minus x naught squared times q of x, in my current context, x not equal to 0 becomes x times 3 over x. And this becomes, x squared times 1 over x squared. So what are we left with? 3, right? And 1. And so, technically speaking, we're thinking about the limit as x approaches x naught as we judge these things, all right? Do you guys know what I'm talking about? Yes, no, maybe so. So these are both analytic at x not equal to 0. So here's another example. Let me divorce the discussion from differential equations for a second here. If we think about the function h of x equal to sine of x over x for x not equal to 0 and 1 for x equals to 0, that function is analytic at 0. Why is that? I mean, it looks like it's got division by 0, but what goes on here, right, is you've got x minus 1/3 x cubed plus 1 over, 120 x to the 5th and so forth, right? And division of series just gives us 1 minus 1/3 x squared plus 1 over 120 x to the 4th plus dot, 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 right? So sine x over x is analytic at 0. To be more careful, it has what's called a removable singularity. The singularity is essentially a hole in the graph. We can just get rid of it by canceling the factor. Yeah. Okay, so example 1, the Cauchy-Euler problem has a regular singular point at 0. Does that make sense? I hope. So here's the big theorem I want to teach you guys. Theorem. Given y prime prime plus py prime plus qy equals to 0, if x naught is an ordinary point, and y equals to, let's say, the sum, and equals 0 to infinity of, say, cn times x minus x naught to the power n, is its solution, then the let me give this I don't want to just call it y. Let me say f of x, if you guys don't mind. F of x equals to that. Then the domain of f of x is as large as it can be without crossing the nearest singularity for y prime prime plus py prime plus qy equals to 0, taken in the complex sense. So that's a mouthful. It's probably best if I illustrate the idea of this theorem with some examples. All right? All right. So let us consider y prime prime plus 1 over x squared plus 4x plus 5, y prime plus 1 over x squared plus 1 y equals to 0. Consider x naught equal to, let's say, minus 3, and x naught equals to 2. Let's find the minimal, not minimal, that's not what I want, maximal open interval of convergence for solution at these x naught. And maybe we'll add another point after we get it all in front of us. So the way this kind of problem is done, we can all do this. We just need to be super careful with the algebra. All right, algebra matters more than calculus in this course, like for sure. So x squared plus 4x plus 5, where is that 0? I complete the square. I have x plus 2 squared plus 1. Right? And so that is equal to 0 when x is equal to minus 2 plus or minus I. These are singularities. These are definitely singularities of that differential equation, right? I cannot calculate the Taylor expansion of that function there. Right? And how about x squared plus 1? That's easier, right? I should have started with that one. X squared plus 1 equal to 0 implies x is equal to plus or minus I, right? So this is also singularity, right? So what we should do is we should graph the complex plane, because that's the thing. Whether you like it or not, we can always extend a real problem to a complex problem, and that complex problem, it's the boss of us, right? It will tell you what you have to do. So if I draw the complex plane, which is just the plane, right? Here's the real axis. Here's the imaginary axis up here, all right? Then what I do is I graph my singular points. So my singular points here are like, minus 2 plus or minus I. So I got like one up here and one down here, right? Minus 2 plus I, minus 2 minus I, right? And I also have two singular points at over here, right? This guy and this guy, right? At I and minus I. I like to use little x's with like circles around them for singular points. I don't know why. It's just what I do. Yeah. It's like, stay away from those points. Danger. All right. Now, x naught, I'm given, right? I'm given that the x naught, which one do you guys want to do first? 2 or minus 3? Minus 3. All right, so minus 3 is like here, right? And then the question is, what is the nearest singularity? Because whatever the nearest singularity is, that tells you how big the solution can be in terms of like its, you know. That's right, yeah. So this one is kind of either here or here, right? And so there's actually a disk. You know, we talked about the radius of convergence in calculus too. This is actually the radius of convergence we're talking about. There's a theorem of complex analysis that says that if you look at a function that has a power series formula, the domain has to be a disk. All right, and that disk will always be as large as it can be without going past the next singularity for the function. And so in this case, the question is, what is that radius here, right? So if we look at this little triangle, the height of the triangle is 1. And I think this distance minus, oh, this is also 1. So the radius of convergence for our power series centered at -3 would be the square root of, well, 2. All right. And so if I was to write f of x is like the sum, you know, n equals 0 to infinity, cn x plus 3 to the power n, this will converge on -3 minus the square root of 2 to -3 plus the square root of 2, at least. I say the open interval of convergence because we're not addressing the question of what happens on the endpoints. You guys remember from Calc 2, it's anybody's guess what happens on the endpoints, right? You remember those problems? We do the, whatchamacallit there, the ratio test, and it gives us the open interval of convergence, and then we have to go back and we have to study the endpoints with like other methods to discern whether or not they're included or excluded. So we're not going to care about the endpoints. I've explicitly asked for the maximum open IOC. Oh, by the way, a nice abbreviation here, interval of convergence. It's so much nicer to just write IOC, isn't it? But so the open IOC is what I'm interested in. Notice that I didn't have to solve the differential equation to answer this question at all, right? We can answer how large the domain is simply on the basis of this little theorem. Okay, so yeah. Now the other point which was given was 2, right? So that's over here. Let me do it in a different color. Markers are suicidal. Let's see here. Ka-chunk, ka-chunk. All right, over here, my other potential place to write the solution is at 2, all right? And so there, again, we're equidistant from both of those singularities. And that's pretty much always going to happen for our examples because we're going to look at real coefficient functions and they always have zeros which come in like conjugate pairs. So it's pretty common. Anyway, so the disk of convergence to the limits of my artistry are like that. What's the radius of convergence for this guy? We've got 1 unit up, right? 2 units over. So it looks like the radius of convergence is 1 squared plus 2 squared, which would be the square root of 5. And so my IOC would be like 2 minus the square root of 5 to 2 plus the square root of 5 for f of x, the sum n equals 0 to infinity of, well, let me use a different letter, b sub n times x minus what? 2 to the power n. This will be one of your most, this will be one of the least, this would be like the warm-up in the boss fight. Like in the boss fight, there'll be one of these, but it'll be like a little baby monster, right? It won't be, you'll conquer this one with ease. And by the way, you guys can work together on the boss fight. Like that's not, you're not to suffer in silence. You can work together. Yeah.
What does it mean when you say at least? Like after you say that?
Because I don't know what happens at the endpoints. So it could be that it includes that or that, but it might not be. I don't know without like a lot more analysis. Now, what if so one last singularity question. What if I tell you your solution has the form, the sum n equals 0 to infinity of like, I guess I'll use a sub n times, x minus 1/2 to the power n. What would the radius of convergence be for this one if it's a solution to that given differential equation? That's what we're talking about. See here, you have to discern what the center of the series is, right? So the center is at 1/2, right? So we would just go, it's like right here, right? And so we'd have to look at like, it would give us like a little, I can't do it worth anything, but so there's like 1/2 is here, the origin's here, I is obviously the closest singularity, for instance. And so what's the radius of convergence for this guy? 5/4, yeah, 1 plus 1/4, yeah, 5/4, very good. It's like square root of 5 over 2 if you like, whatever. But okay, so that's the deal with singular points. That's pretty much, what I have to teach you about that. Now, Frobenius theorem, I'm going to use the projector for this, and because it's a lot. However, it really is not. Here's the thing, is this Frobenius method I'm about to show you is entirely the same as what we've done up to this point, with one teensy weensy itty bitty adjustment. And let's see if you guys can see what it is once I get it out here. Now, the Frobenius method is something I would only ask in the take-home format at the moment. I would not ask it in class. So it might appear in your boss fight, but it wouldn't appear on the final, all right? Because it does require significant concentration, in my experience. But it's important in terms of, there's a number of, central mathematical physics problems that we need this method to solve. Like I said, Bessel functions would be an example. I can find my notes, that would be helpful. I've got everything open except for your notes. Did you guys hear about the 7 that had a cold?
The what?
The 7 that had a cold?
No.
No. It was a 6-7.
Did you come up with that?
I did not. That's not mine. I have to give credit where credit's due. That's from the associate coach at the YMCA.
That's truly unfortunate.
Apparently, he is known for this. For 6-7 jokes particularly. That's his specialty apparently. Is it doing this thing again? Come on. Recognize. Hello? There we go. Oh, cosine Laplace. Now Laplace transforms, that will be on the final, right? For sure. Definitely on the final. All right. So this is Frobenius method. Basically, Frobenius method answers the question of how do we solve a differential equation at a regular singular point? All right? How do you solve a differential equation at a regular singular point? And so here's the thing. We're given y prime prime plus py plus, py prime plus qy equal to 0 with x squared p of x and x squared q of x analytic at x equal to 0, right? What that means then is tracking back that you could have written p of x like this, and you could have written q of x like this, all right? And at least one of q naught, p naught, or q1 has to be non-zero for it to be actually a singular point, all right? These, by the way, are what are known as Laurent expansions. If you take Math 331, we study how to use Laurent expansions to do integrals. If you're going to go to graduate school in engineering, you really should consider taking Math 331. That kind of mathematics is actually important for like higher engineering. Anyway, because it really completes the story of how to do calculus in the complex plane, and many things are known that you'd like to know. Anyway, so the point is we have this and that are given Taylor expansions for xp of x and x squared q of x, right, because they're analytic. And listen, we're just going to assume that x naught is equal to 0 to reduce clutter. This whole thing could be done at x naught not equal to 0, but it's just much cleaner to focus on x equal to 0, all right? So the Frobenius solution at a regular singular point, in particular at 0, there exists a number r and coefficients a sub n such that y equals sum n equals 0 to infinity of a sub n x to the n plus r solves the thing. Isn't this just what we've been doing? What's the difference? What did we assume before the test when we worked on, we worked out a couple of these, right? In gory detail with the recurrence relations and all that, remember? The difference, just a tiny little difference, we didn't have plus r, right? We just had n. What's the difference if you add the r? Well, we'll see. So we can denote the solution as like y of r comma x. R is called the index of the solution. And it turns out that you can do term-by-term calculus. So like the derivative is just what you'd think it is, n plus r times x to the n plus r minus 1, and differentiate twice. You bring down two factors, just like you'd expect, all right? These are not power series, though, see, because r doesn't have to be a whole number. R could be a half. R could even be complex, all right? It's just a number. And so if you take those, though, and you plug them back into the differential equation, which is just the method we've been doing already, right? Take the series, that's the solution, plug it into the differential equation, face the music, right? See, we actually have to multiply the series expansion for xp of x and the series expansion for x squared q of x times our Frobenius solution. By the way, these are called Frobenius solutions. So how does that work out? Well, you got to go order by order, right? So if you study this, just writing it out again, I think I re-indexed. What I did was did I do anything? I don't know if I did anything. Oh, that's y prime prime. I think what I've done, well, hold the phone here. Huh. I feel like, oh, I'm an idiot. So we had an x squared. Like we multiplied the whole, sorry. So we started with y prime prime. Oh, okay, I see. I'm sorry. I'm losing track of what I did. I multiplied the differential equation by x squared, right? And that's why there's not a minus 2, because this x squared times that gave me an x to the n plus r, right? And then this x times that ended up giving me the that, right? Where's the other x gone to? The other x has gone into making this analytic, right? And the q expansion eats up the x squared, right? That's why we have matching n plus r, n plus r, n plus r on the next page. I thought it was a mistake, but it's not a mistake. I just was smarter when I wrote these notes. So there you go. And great. So you've got this sum of series. And the only way that can be equal to 0 is if every single component independently vanishes, right? And so if you look at that, n equals to 0 gives us the lowest order terms. So n equals to 0, which would be the coefficient of x to the r, I pick up a sub 0 times this, plus p sub 0, a sub 0 times that, plus that. And so you see that the value for r has to be chosen such that this equation holds true. If you go and look at the Cauchy-Euler problem, that's exactly the characteristic equation of the Cauchy-Euler problem. The Cauchy-Euler problem's characteristic equation is the indicial equation of the Frobenius method as it applies to this case. So that's a quadratic equation in R, so it has two solutions, right? Which gives us two indices, and then we just have to like plug those in and work it out, which means that we have to solve these lovely equations. Here's an example. 3x y prime prime plus y prime minus y equals 0. X equal to 0 is regular singular point. I write down my Frobenius solution. I plug it in, differentiate it, multiply by the x, put it all together. It gives me this beastly thing. I think I'm missing a 0 over there. And so the indicial equation here is that, right? And also, since I did the math like this, I can like read off that the recurrence relation for a sub n and a sub n minus 1 over there. You see I solved that to find this relation between the coefficients. I did it for an arbitrary r. That way I can then go and use the solutions to the indicial equation to get two separate recurrence relations, one for each root of the indicial equation. And so I sort through that, kind of like we did the other class, and I get these particular lovely relations. And lo and behold, the 2/3 index gives me this solution. Yay. And the other one, r equal to 0, well, that actually gives me a power series solution. So the general solution then looks like this. This is not a power series, right, folks? Like, we're talking about sums of the 2/3 power of x. And then this has got like 5/3. And what's 2 plus 2/3? 8/3. Yeah, I mean, like all of these fractional powers of x. What's the domain of those kinds of things? Did you ever think about this? What's the domain of the Cauchy-Euler problem? So the solutions we wrote down, they were true either for positive x or for negative x. We pretty much always worked with positive x, but technically speaking, you go in either way. Likewise, these, as I've set it up, are defined for all positive x. 0 is a singular point, right? This is not a power series solution, right? The domain theorem I was talking to you guys at the start of class doesn't apply here because what we're looking at are not power series. It's a Frobenius series. And so like the structure of its convergence is very different. Anyway, so there's one. Here's another one. X squared y prime plus this. So you like basically look at the indicial equation. This one has a repeated root of -1. Ugh, that's unpleasant. And plugging it in, I end up with like, this is my recurrence relation. And this one is a Cauchy-Euler problem. So something cool happens in this one. The recurrence relations truncate because like the Cauchy-Euler problem doesn't have an infinite series of power functions. It just has like 2 power functions for your general solution, right? So what happens to the method of Frobenius is when you work through the details, like everything crashes out except for like the first 2 terms. That's it. And well, we remember when we have a repeated root, we had to do the repeated root thing. So somehow natural log comes into the scene. This one, we have imaginary indices, this one. And so it's kind of, you get complex recurrence relations. And I don't have a complete, I don't have like a full power series answer for one of these. This is the best I have at the moment. So you like basically, you know, put the imaginary part over there, the real part over there, x to the 2i, but we know x to the 2i is, you know, cosine 2 log x plus I sine 2 log x, and the x to the n just comes out. So I take that complex expression and I multiply it by that complex expression, and it gives me a real part and an imaginary part. Those are separately the real solutions. Same thing as usual. We find a complex solution, we pick off the real part and the imaginary part. Those are your separate solutions. This one's hard, I think. So when I first started teaching this course, like I lost days to this problem, right? Like in the summer, I'm like, oh, Frobenius method. I don't remember that from my class. What is that? And then, why doesn't it work? Like you have to be so careful. It's so easy to mess these up. But now you guys have ChatGPT, right? So it'll steer you right. Probably not. I don't know. I'm not sure. Can ChatGPT do the Frobenius method? Well, you guys will find out, I guess. But I mean, you can try. I just, you know. So anyway, I want to talk to you guys about this, and I'll let you explore like maybe a problem or two in the boss fight about this, but that's kind of as far as it goes. But I want you to be aware of it because there's whole vistas of other problems that you can now solve with this method. You just have to try it. And also, it will make, if you find yourself working on a specific problem and you have to look up in a table somewhere special functions, odds are very high that those special functions are defined by the Frobenius method. Anyway, I have your test to give back to you, so let me do that. And I'll shut up for today.